Right, looking at points in 3D here. Now, points in 3D, very similar to points in 2D, but we have a third dimension. So we're used to seeing the x-axis and the y-axis. In 3D, we also have a z-axis. So we've got three parts to the coordinate. So if I sort of try and draw a 3D coordinate, this is a bit of a weird thing because they don't really look right. Anyway, I'll show you what we mean by this 0, 4, 2. So I'm going along 0, up 4 on the y-axis, and then along 2 on the x-axis. So on the z-axis, sorry. So that coordinate would be here, 0, 4, 2, along 0, up 4, and then along the z-axis 2. If I now show you this next coordinate, 1, 4, minus 2, along 1, up 4, and then minus 2. So it's kind of going like that, somewhere there. Now the problem with this is I can't really tell where these coordinates are in three-dimensional space because I'm looking at a two-dimensional view. So when we get to 3D coordinates, really the plotting of them is done with technology in 3 dimensions. However, we can calculate a number of things using those 3D coordinates. For example, we can calculate the distance between 2 points. So if I want to know the distance between point A and point B, I need to consider the cuboid formed in those 3 dimensions. Considering the cuboids allows me to find these distances. So if I want to find the distance between A and B, well, I could find, first of all, the distance across the base here using a bit of Pythagoras. And we form lots of right-angled triangles in a cuboid. In fact, all the angles in a cuboid are right angles to begin with. So if I know this distance and this distance, I can work out the diagonal across the bottom. Well, this distance here is going to be the difference between this one and A there. So it's just going to be the difference in my z coordinates. So we're going from 0 to 2, and so this is a length of 2. This distance along here, that's going to be my difference in my x coordinates from here to here. And well, on the x I've gone along 8, so from 0 to 8 that's a distance of 8. Now that I've got this, I know that this will be the square root of 8 squared plus 2 squared using Pythagoras. Now to find this diagonal, the AB, I'm also going to need this length, and that is the difference in my y coordinates. Well, that has gone up 6. So I now have a right-angled triangle going in here. So that right-angled triangle, I'm going to square this. Well, when I square it, I just get rid of the square roots. So I end up with 8 squared plus 2 squared plus 6 squared, and then square root that answer. So with a cuboid, what I can do is I can just take all 3 dimensions, the length, the width, and the height, square them all, add them all together, and then square root to find the length of AB. So any diagonal from corner to corner through a cuboid, we can take the 3 dimensions, square them all, add them together, and then square root. And in fact, here is the formula for when we're doing in 2 dimensions. It's Pythagoras basically, isn't it? So the difference in the x coordinates, the difference in the y coordinates, that gives us the difference in the x coordinates, the difference in the y coordinates. With 3 dimensions, we need to bring in the difference in the z coordinates. Other than that, it's going to be basically the same. So you square the x coordinates, square the y coordinates, difference in the x, difference in the y, difference in the z, add them all together, and then square root that answer. And that will give you the distance from one point to another in 3 dimensions. Okay.